Hello everyone, my name is Ngan and I'm a research assistant in Department of Computer Science. I work under Professor Terence Sim's supervision. Our research topic is about estimating total body surface area using subject-specific feature. Here is the outline of my talk today. So I will start with the motivation of this work. During their lifetime, humans may encounter accidents that leave wounds on the body, such as burn wound, hides, and strangle with different severity levels. Those wounds need to be diagnosed by doctors before applying appropriate treatment. Initially, doctor will need to analyze the wound condition, such as its location, shape, and size. After that, they will need to measure the severity of the wound with respect to the total body surface area, or TBSA. One standard way of measuring this severity is by computing the percentage of the wound size over the TBSA of a specific patient. For example, a wound size that covers 0.06 meters squared of a patient body with TBSA equal 1.54 meters squared means that the wound size is about 3.91% of the TBSA. Intuitively, the larger the percentage of the wound size over TBSA means the more chronic it is. This measurement is useful as the same wound size on a child can be more serious and require more care compared to the same one on an adult. Even for adults, not everyone has the same body shape, so the TBSA varies between different people. Therefore, accurate TBSA estimation is an important aspect of this formula to correctly evaluate the severity of wounds. So previous work can be divided into two groups, namely generic and specifics. The first group includes methods that use generic human figures like rule of knives, line and border chart, rule of palms. In general, they assign fixed percentage of each body part to estimate the percentage of TBSA. Let me explain the difference between these methods in more detail. So for rule of knives, it divides body surface into smaller regions that covers around 9% of the body surface area. The front of head, back of the head, both arms, front legs, back legs, chest, abdomen, upper back, and lower back. On the other hand, line and border chart provides a more detailed division for different regions on the body surface by dividing human body into more regions as compared to the rule of knives. Most importantly, it considers the different percentage of the head, thigh, and lower leg over different age groups. 0 is year old, 1, 5, 10, and 15 years old. Meanwhile, rule of palms is the simplest one compared to other methods. It only uses the size of a person's palm to determine how big is the wound size over the TBSA. And it was based on the observations that the palm of an adult with and without finger is around 0.8 and 0.5% of the surface. The corresponding value for a child is 1 and 0.5%. Note that none of these methods give the exact values of TBSA, only the percentage of the body that the wound covers. Also, they only use a generic human figure and don't consider the detailed variation between different human bodies. So to eliminate these issues, formulas that predict a patient TBSA based on his or her specific height and weight were proposed by other researchers. They use this nonlinear equation with different values of A, B, and C that derived from each researcher experiment. The constant A and B describes the importance of height and weight. For example, boys assign higher importance on weight than height. On the other hand, equation 5, 6, and 7 assign higher importance on height compared to weight. It assigns equal importance on weight and height. Using height and weight instead of generic human figure is better for estimating TBSA. It's more accurately as they consider patient-specific features that are different across patients. However, none of the previous methods yield visual features that should be more specific than height and weight features as person, face, and hand to help predicting the TBSA. Therefore, our research aims to combine the visual feature extracted from face and hand with height and weight feature to provide a better estimation of the TBSA. Since there is no available data that contains both body scan and visual feature like face and hand photo, we started with collecting a new dataset that includes TBSA values along with other metadata of a human subject. For each subject, we collect his age group, gender information, measure the height and weight. Then we take a photograph of the subject's upper body and crop out the face and hand region from the photograph. For the TBSA value, we used a 3D body scanner from TG 3D company. So this is a picture of the scanning room. This is a model of the scanning room. It has 4 sensors at the top corners that emit near-infrared light to capture the 3D shape of a subject. The output of the scanning process is a point cloud that it captures the entire human body surface. Then we propose a regression model that estimates TBSA using the collected data, which is summarized by these figures. This model had 2 stages, training and testing. In training, we extract visual features from the hand and face photograph, the training dataset, and use them with height, weight, and gender information as input feature to the model. I can describe the visual feature extraction in the next slide. From the point cloud output of the scan, we create a 3D mesh using a surface reconstruction method in MeshLab. Then we can easily compute the TBSA value as the total area of all triangles on the mesh. We consider this TBSA as a ground truth, and they are used in the training stage as the desired output of the model. In testing stage, given the visual feature, along with height, weight, and gender of a new subject, the regression model predicts the TBSA value of that subject. Note that during testing, we don't need the 3D scan of the patient. So this model can be used in small clinic or even at the patient's own house. For the face and hand photographs, in order to eliminate the inconsistent distance between camera and the subject during data collection, in case the subject have different face expression, we need to normalize all face and hand photo to a single reference face and hand photos. Specifically for each face, we choose 3 points on the face and map them to the corresponding point on the reference photo using a phase transform method. The same procedure is applied to the hand photos. The consist points are stable points. The stable points are chosen as points that are not easily altered due to skin movement, such as change of face expression or hand movement. For the face, the stable points are 2 points at the center of the eyes and 1 point at the center of the nose. For the hand, 1 point located near the bottom left corner of the index finger, another point located near the bottom right corner of the pinky, and last point located near the bottom left corner of the palm. After normalizing face and hand photograph, we extract their features. The face and hand features are determined as follows. Face feature is determined by 30 landmark points that are placed on the outline of the face, the nose, and the 4 corners of the mouth. For the hand, we use 3 types of feature. The first one consists of only 5 fingertips. The second one consists of 9 points along the outline of the palm, and the last one includes all points in the previous two. In our experiment, we collected data of 21 subjects that consists of 10 female and 11 male. For each subject, we collected the photographs and information as I described previously. The body mass index, BMI, and TBSA range of female and male subjects are in this table. So as we can see, both genders has mean BMI around 23, with female BMI varies more than male BMI. Almost all of them have a healthy weight, except for only 2 female subjects who are overweight. Meanwhile, the female group has much smaller TBSA, around 20 centimeters square less than the male group's TBSA. Since body composition of male and female are usually quite different, we use 2 separate regressions, one for each gender. Each model will take a combination of visual features, which can be either the face features or one type of head features, or both face and hand features. We use a linear regression model, and since we were only been able to collect data of 21 subjects, we use live-on-our method to split the data into gene set and test set, and sequentially compute the predicted TBSA for every subject in the entire dataset. The prediction error for the model is measured as a percentage of the difference between the predicted TBSA value and actual TBSA value over the actual TBSA value. So this table summarizes the error percentage of the model for each gender group with different combination of visual features. As we can see, the average error percentages are less than 10% for both genders. The model always performs slightly better on male group compared to female group, except when only face feature is used. The smaller average errors for female and male group are 3.2 and 1% respectively, and they are obtained with fingertips as the only visual features. We can also see that the difference between max and mean error obtained using fingertip as the only visual feature are much less compared to other visual features for both genders. For instance, using palm region feature as visual feature has the smallest error as 0.45%, half of the fingertips minimum, but the maximum error is almost double fingertips. This means using fingertip feature with height and weight consistently give a better prediction for both genders. So to understand the effectiveness of our model, we compare it with previous methods. As we recall, there are 2 groups of previous quotes. One using generic human figure and only gives the percentage of one's body part to the TBSA, not the exact TBSA value. The other use height and weight, which are subject-specific data. Therefore, in here, we only compare our results when using fingertips as the only visual feature with the second group that uses height and weight. Here's a comparison table that shows the mean error percentage and the standard deviation of each method. As we can see, our model gives the smallest error out of 6 methods for male group. But for female group, both methods give the smallest error. The standard deviation of all methods are similar, so besides the average error, we also want to know how many subjects that our model gives the closest TBSA prediction, the number of subjects with minimum error across methods. In this table, we can see that for female, our model gives the closest prediction for 3 out of 10 subjects, same number as both methods. For female, ours give much better prediction, 8 out of 11 subjects. In total, over 21 subjects, our model gives the best prediction for 11 subjects, over 50% of the data collected. Therefore, we can say that the proposed models give an overall the closest TBSA prediction. However, for the case when our model doesn't perform well, the error is usually quite big compared to, let's say, Boy's method. This may be due to the limited data that we have. We only have a small number of subjects with HA that range from 20 to 60. In conclusion, we find that for our dataset, fingertips is the most important visual feature for both female and male subjects. Also, proposed model gives the best TBSA prediction for most subjects compared to previous work. In the future, we will collect more data, especially with large variation of body weight, so that we can study the effectiveness of the proposed visual features. Also, for the hand, instead of just using the shape features, we incorporate the texture of the hand. This may improve the TBSA prediction. That's all for my presentation. Thank you for listening.